For centuries, humanity believed the structure of our own planetary system was typical. The arrangement of small rocky planets close to the star, large gas giants farther away, and icy worlds in the outer regions seemed logical and orderly. When astronomers began discovering planets around other stars in the 1990s, many expected to find similar systems scattered across the galaxy. But the deeper scientists looked into the universe, the more they realized something strange. The most common type of planet in the galaxy doesn't exist anywhere in our own solar system. That realization has forced astronomers to rethink long-held assumptions about how planetary systems form. The discovery of exoplanets, planets orbiting stars beyond our sun, changed astronomy almost overnight. In 1995, astronomers confirmed the first planet orbiting a sun-like star outside our solar system. The planet, known as 51 Pegasi b, stunned scientists because it was completely different from anything seen before. Instead of orbiting far from its star like a typical gas giant, this planet circled extremely close to its star, completing an orbit in just 4 days. The discovery of this so-called hot Jupiter immediately showed that other planetary systems might be radically different from our own. As telescopes improved and detection methods became more sophisticated, astronomers began discovering thousands of new exoplanets. Missions like Kepler Space Telescope monitored hundreds of thousands of stars, searching for tiny dips in brightness caused when planets passed in front of their host stars. These transits allowed scientists to estimate the size and orbit of distant planets. Over time, a surprising pattern began to emerge. Most planets discovered by the Kepler mission were neither Earth-sized rocky planets nor massive gas giants like Jupiter. Instead, the majority fell into a category called super-Earths, or mini-Neptunes. These planets are larger than Earth, but significantly smaller than Neptune, typically between 2 and 4 times Earth's radius. What makes them remarkable is that they appear to be extremely common throughout the galaxy. A super-Earth is generally defined as a planet with a mass several times greater than Earth, but still composed largely of rock or dense materials. Mini-Neptunes, on the other hand, are similar in size but contain thick atmospheres of hydrogen and helium surrounding a dense core. Both types appear frequently in other star systems, yet our solar system contains nothing quite like them. The absence of these planets in our own system is one of the biggest mysteries in planetary science. Between Earth and Neptune lies a massive size gap. Earth has a radius of about 6,371 kilometers, while Neptune's radius is more than 4 times larger. But in many other planetary systems, planets exist in this intermediate size range. This raises an intriguing question. Why does our solar system lack the most common kind of planet in the universe? One possibility involves the early formation of the solar system. Planetary systems form from enormous disks of gas and dust that surround young stars. Within these protoplanetary disks, particles collide and gradually build larger bodies known as planetesimals. Over time, these bodies merge into fully formed planets. The exact conditions within the disk, such as temperature, density, and chemical composition, can influence the types of planets that eventually emerge. Another major factor may have been the role of giant planets like Jupiter. Jupiter's enormous gravitational influence likely shaped the development of the entire solar system. Some scientists believe Jupiter migrated inward during the early stages of planetary formation before moving back outward again. This movement could have disrupted the formation of super-Earth-type planets near the Sun, preventing them from fully forming. This idea is sometimes called the Grand Tack hypothesis. According to this model, Jupiter initially moved closer to the Sun due to interactions with the surrounding gas disk. Later, the formation of Saturn altered the gravitational balance, causing both planets to migrate outward. If this theory is correct, Jupiter's migration may have scattered or destroyed any developing super-Earths in the inner solar system. Another explanation suggests that super-Earth simply never formed here because the building blocks were distributed differently in our solar system's early disk. Planet formation is a chaotic process influenced by countless collisions and gravitational interactions. Even small differences in the initial conditions could produce dramatically different planetary systems. Observations from missions such as TESS continue to reveal just how diverse planetary systems can be. Some stars host tightly packed systems with multiple super-Earths orbiting extremely close to their star. In some cases, several planets orbit closer to their star than Mercury does to the Sun. These compact systems challenge our understanding of how planets migrate and settle into stable orbits. One particularly fascinating example is the TRAPPIST-1 system, which contains 7 Earth-sized planets orbiting a small red dwarf star. The system's compact arrangement and multiple potentially habitable worlds have made it one of the most studied planetary systems beyond our own. Although these planets are roughly Earth-sized rather than super-Earths, the system demonstrates just how different planetary architectures can be. The existence of super-Earths also raises important questions about habitability. Larger rocky planets may have stronger gravity, thicker atmospheres, and potentially more stable climates. Some scientists believe these conditions could make super-Earths excellent candidates for life. However, if the atmosphere becomes too thick or the internal heat too intense, the planet could resemble a hostile world more like Venus than Earth. Interestingly, some researchers believe that the absence of super-Earths in our solar system may actually have helped life develop here. If a massive super-Earth had formed close to the Sun, its gravity might have destabilized the orbit of Earth or prevented it from forming entirely. In that sense, the unusual structure of our solar system may have been essential for the existence of life on our planet. Another puzzle involves the composition of mini-Neptunes. Many of these planets appear to have dense, rocky cores surrounded by thick hydrogen-helium atmospheres. Some may have formed as small gas giants that never accumulated enough mass to become fully developed giants like Neptune. Others may have formed as rocky planets that later captured large envelopes of gas. Scientists are still debating which of these formation processes is most common. The answer may depend on factors such as the distance from the star, the age of the planetary system, and the properties of the surrounding gas disk. Understanding these processes could help explain not only why super-Earths are so common elsewhere, but also why they are absent in our own system. The study of exoplanets has also revealed that many planetary systems undergo dramatic migrations and rearrangements over time. Planets can move closer to their star or shift outward due to gravitational interactions with other planets or with the protoplanetary disk. These migrations can completely reshape a system's architecture, creating configurations that would never arise from simple formation models. Because of these discoveries, astronomers now realize that our solar system may be somewhat unusual. While it is not unique, its structure, small rocky planets followed by distant gas giants, is not the most common arrangement in the galaxy. Many star systems appear to be dominated by super-Earths or tightly packed planetary groups. This realization presents a challenge for planetary science. For decades, models of planet formation were based primarily on the structure of our own solar system. Now scientists must revise those models to explain a much wider range of planetary environments. Future missions may provide more clues. Advanced telescopes will allow astronomers to study the atmospheres of distant exoplanets in greater detail. Instruments such as the James Webb Space Telescope can analyze the chemical composition of exoplanet atmospheres by examining the light that passes through them during transits. These observations could reveal the presence of water vapor, methane, carbon dioxide, or other molecules associated with planetary processes. As scientists continue exploring the universe, they are beginning to see planetary systems not as predictable structures, but as products of chaotic cosmic evolution. Each system represents a unique combination of initial conditions, gravitational interactions, and environmental factors. The surprising abundance of super-Earths reminds us that our solar system is only one example among billions in the galaxy. While it may seem ordinary from our perspective, it might actually be somewhat rare on a cosmic scale. Another important reason the discovery of super-Earths has puzzled scientists is that their internal structures may be very different from anything found in our solar system. On Earth, the planet's interior is divided into several layers: a solid crust, a mantle of slowly flowing rock, and a metallic core made primarily of iron and nickel. This layered structure drives geological activity such as volcanoes, earthquakes, and plate tectonics. But super-Earths, because of their larger masses and stronger gravity, may behave very differently inside. When a planet becomes several times more massive than Earth, the pressure inside its interior increases dramatically. The materials that make up the mantle may be compressed into exotic high-pressure mineral forms that do not exist naturally on Earth's surface. Some models suggest that the deep mantles of super-Earths may become so dense that convection, the slow movement of hot rock that drives plate tectonics, could behave differently or even stop entirely. If that happens, the surface of the planet might lack plate tectonics, which on Earth plays a key role in regulating the atmosphere and recycling carbon through geological cycles. On the other hand, some scientists argue that larger planets might actually have more vigorous tectonic activity because their interiors retain heat for longer periods of time. The stronger gravitational forces could create higher internal pressures that generate powerful mantle currents. If that is true, super-Earths could have extremely active geological surfaces with constant volcanic eruptions and rapid recycling of crustal material. This type of activity could potentially maintain thick atmospheres and stable climates over billions of years. Another intriguing possibility is that some super-Earths may be dominated by enormous global oceans. Understanding why our solar system lacks the most common type of planet could reveal important insights into how planets form, migrate, and evolve. It may even help scientists determine how common habitable worlds truly are in the Milky Way. In the end, the mystery of missing super-Earths highlights something fundamental about science. Every discovery raises new questions. The more we learn about the universe, the more we realize how much remains unknown. And somewhere among the countless stars of the galaxy, there may be planetary systems whose structures are even stranger and more fascinating than anything we have discovered so far.